So this is recording 2 of topic 8. So using probability to make decisions about data, right? So this is beginning of hypothesis testing, which we'll cover in the next lecture. So we stopped on this slide, right? And the next is why. Why do we even care? Okay. Basically, the essence of inferential statistics is deciding whether a sample of scores is likely or unlikely to occur in a particular population, right? And to understand this, we have to remember that any sample may poorly represent one population or may accurately represent another. So I'm going to try to draw this, even though this is terrible on this, but it's really important. So for example, let's say we get a lot of data and we get these data points. So whatever value this is, okay, and we take the mean of this. So we're going to take their mean, right? So we don't know necessarily what population these guys come from. It could be that these are actually all scores from a population with their mean, that's with the mean that is equal to their mean, right? Right? So this means it would accurately represent this population, right? But what if these scores come from a different population? What if they come from this one where the true mean is over here, and these are just scores that are extreme, right? They're much lower than the true mean. This means that these scores are a poor representation. They poorly represent this population, okay? And what we're going to be doing is trying to figure out if when we have a sample and we get a mean or whatever we're looking at, if that sample mean is likely to represent one population or a different population, right? Okay, so moving on. Just as a review, definition of inferential statistics, procedures used to make generalizations about a population from a sample of that population. So we've talked a lot about election polling. We have an election coming up next year. Okay, they'll ask 1,000 people how they will vote, and then they'll say, oh, well, the vote's going to be this way. See this all the time, right? We're going to use it for hypothesis testing. We're going to start out with t-tests, and then we're going to move on to, well, we're going to start with Z actually next week, and then t-tests, and then ANOVA and so forth. Okay. And we see this a lot in, popular press. We might see something like representative prevalent surveys in which a random group of people are selected for coronavirus testing. Okay. So let's think of that. Think about that. There are some important terms here. A representative sample accurately reflects the individual's behaviors and scores found in the population. So in our example, it was the curve when I showed you what the mean would be. It's with the mean of the sample is more or less equal to the mean of the population, right? Random sampling, that just means that all the individuals in the population have an equal chance of being selected, and they're selected at random, right? And we took the example of polling where a long time ago, 99% of the US population had a landline and there was only AT&T. So a polling company could randomly select phone numbers and get a pretty good representation, right? Now, well, half people don't have landlines. People with cell phones might not answer unless they recognize the caller. So it's much harder to get a representative sample now for polling because that randomicity might not actually happen. Not everybody has an equal chance of being selected. If they're using cell phones, everyone who doesn't have a cell phone doesn't have an equal chance of being selected, and vice versa for landlines, right? Now, this should be distinguished from random assignment. This is just when you bring people into the lab or have them do an experiment wherever, maybe on Qualtrics, you can do it there too. And every participant in the experiment has an equal chance of being in either group, if there's 2, or any group if there's 3 or more. Right? And we can use random number generators to do this. We can have a survey platform such as Qualtrics randomly assign people to groups. The idea is this controls for any pre-existing conditions, personality traits, and so forth that might affect the outcome variable. So let's think about what that might look at. So for example, here we have student demographics of California community colleges by ethnicity in 2019 to 2020, right? So we see that overall we have 46% Hispanic, 23% white, 11% Asian, almost 6% African American, and so forth, right? So if we get a sample of California community college students, we want the proportion in the sample, the proportion of these different ethnicities in the sample to more or less reflect the same thing as in the population so that it's representative. We want about 46% Hispanic and so forth, right? So why is this so important? Because if we want to learn about population basis samples, we want our sample to accurately reflect the population. What happens when it doesn't? Well, a lot of things can happen. For example, for decades, medical trials would not use women in the trial. Why? Because female hormones, right? Menstruation supposedly caused female emotions to vary, and that made psychologists not want to use women. And for medical trials, they thought, well, because female, we don't know what's going on in their body, they might react differently to the medication, with the result of a lot of things being understudied for women. Take heart disease. All of our diagnosis, identification of, and treatment of heart disease up till very recently was based on trials run exclusively with males. So this means that female heart disease is underdetected in a lot of different things. It's not necessarily treated optimally and so forth. So another example where we might, we've talked about in this class, we've talked about the hypothesis that violent video games cause aggression, right? And we talked about the group of researchers headed by Anderson that has claimed persistently that violent video games cause aggression. Well, here's another group that has dedicated itself to showing that this might not be true and that perhaps their samples aren't representative, right? And let's just look at this. 2 studies examined the relationship between exposure to violent video games and aggression in the laboratory and in real life. Study 1, participants were either randomized or allowed to choose to play a game, a violent or non-violent game. Although males were more aggressive than females, that's normal, more testosterone, right? Neither randomized exposure to violent video game conditions nor previous life experience or previous life exposure of violent video games caused any differences in aggression. And they found a similar thing in study 2, right? These results question the common belief that violent video game exposure causes violent acts, right? So I'm going to use this next slide because it's white, even though we're not going to do a discussion here because I'm just recording this video. But we're going to think a little bit about something like an experiment. So if you believe that violent video games, such as, say, Grand Theft Auto, cause people to be more aggressive, you are proposing that there is a population of people who play violent video games, right? This population of people who play violent video games, their mean aggression score, somewhere around here, you're proposing that it is going to be higher than a separate population because they come from different population. There will be a separate population of people who do not play violent video games, and their mean aggression score is going to be much lower, right? You can see in my hypothetical distributions here, theoretical distributions, that this mean is much higher. So if this were the case, then the mean of this population of the Tetris players is going to be much lower, Tetris, than the Grand Theft Auto player. We're hypothesizing that these are different populations, right? Actually, it's a little bit more complicated. We're hypothesizing that the difference between the means comes from one population or another. But for a demonstration, we're just going to look at that. But what if we have everybody play and then we collect mean aggression and the mean is about here for both groups, right? Both groups. We have Grand Theft Autos maybe about here and Tetris maybe about here. Well, this would be evidence that actually they're coming from the same distribution, right? Oops. Oh dear. I accidentally went forward. Let me go back to my, okay. They come from the same population, right? So basically we do this by making guesses about a hypothetical, right? A theoretical distribution of scores, and we test whether the likelihood of a sample mean we get belongs to one distribution or the other, right? So we could talk about the distribution of the differences between the means, and we'll be doing that later, right? We're going to start simple by just doing one sample test, right? Okay, so moving on. So we would have had a brainstorming session about why number of reported COVID cases might estimate as we expect it does. Well, that's because whose COVID data is reported? People who must test and report, and people who voluntarily test and report. But people who refuse to test and report, people who cannot test and report, and people who don't know anything about it, well, their data is not included, right? When we look at all these national reports, right? We should have everybody's, right? But we don't. And why this is important is because we base our inferences on the sample, and if it's not representative, then we're not going to get an accurate view of the population, right? Okay, so moving on. Again, representative sample, just accurate individual scores in the sample, and scores in the sample accurately reflect the characteristics of individuals and scores in the population, right? Sampling error happens when random chance produces a sample and sample statistic that is not equal to the population parameter it represents. And sampling error can come from all sorts of different causes, right? So small sampling error is much more likely in small samples. Why would that be? Well, just think about it, okay? For us to get, here we have, the mean. So if an accurate sample might be all here, but what if we collect a small enough sample that all of our participants can be extreme scores, right? So if there's a big sample, there's just not going to be as many, it's going to be better representative because there just aren't that many extreme scores to select from, right? So sampling error always more likely in small samples. So the bigger sample you can get, the better, right? But how do we decide if a sample is representative? Okay, and this is what we're going to be doing really next week, but I'm going to walk you through this now. All right, so we use probability to decide if a sample is representative of the population that we're targeting, right? So basically, we are estimating the probability of obtaining the data from our sample, right? If the null hypothesis were true. So a null hypothesis is just a theoretical distribution that reflects what the data would look like, what the proportion of scores would look like if it was not how we expected, of no effect, no relationship, and no correlation. So as researchers, we want to reject the null hypothesis. Basically, we're testing whether something we don't believe is true. If we have evidence, we're testing if we have evidence that something we don't believe is true is in fact not true, right? The null hypothesis is always of no effect, no relationship, and no correlation. So let's actually draw a picture of this. Okay, so we've talked about correlations, right? We've talked about how, for example, you guys are probably sick about it, we've talked about the relationship between moral identity and aggression, right? Right? And we could hypothesize that that's a negative relationship, right? The greater the sense of moral identity, the less aggressive people are going to be, right? So this would be our hypothesis, right? Our hypothesis would be a negative relationship. The null hypothesis would be no relationship. And as you might recall, no relationship is just a flat line, which means that we cannot tell anything about aggression based on scores and moral identity, right? So that will be an example for correlation. So let's go back to our video game hypothesis, right? So if we believe that violent video games cause aggression, then we can have this is aggression over here. Here we have Grand Theft Auto. And here we have Tetris. So our hypothesis, our research hypothesis, is that aggression will be greater for people who play Grand Theft Auto than for Tetris. our null hypothesis is of no effect. So the null, this is the null, would be that the means for Grand Theft Auto people and Tetris people, this is aggression, right, are going to be the same, okay? Right? So the null hypothesis is denoted H sub 0. And this is just that there's no difference between the mean, and the alternative is H sub A or H sub 1, right? And we'll get back to that next week. Okay, so let's go back to our PowerPoint. Okay, so in other words, we test the probability of our data looking like it does in the sample if they did not look that way in the population that we got the sample from, right? So what does this mean really, okay? This just means that we are going to reject the null hypothesis if the data required would be so unusual in the null, under the null hypothesis, if the data will be so unusual that it will be very improbable and fall in what we call a region of rejection. So for example, we collect a sample and we take the mean of the sample, right? And then we calculate the z-score, which we'll be doing next week, right? And we find a mean that is 2.5 standard deviation. Our sample mean is 2.5 standard deviations above the mean. So approximately right here, right? So this will be very, very unlikely. If this is our null hypothesis, our null distribution, right? If we get a sample mean that's way up here, if it belonged to the null hypothesis distribution, it will be very, very unlikely, right? More likely is that it will belong to a different population with a mean over here. Okay, hopefully that makes sense. This is hard to do without students. Let me get rid of these guys. Okay, let's do it again. Or for example, I was walking you through an example. Say I'm testing whether my statistics teaching is decent, and say we have a national average of mean on a statistics test in this semester at 75. And I have all of you guys take a statistics test. And unfortunately, national average, we're going to say population mean is 75 and population standard deviation equals 5. And I have you guys take the test and say you get a 70. All right, that's below average, but maybe it's just sampling error. So I change this into z-score. 70 minus 75 divided by 5 is -1. -1. Look, getting a z-score of -1 is actually not very unlikely. There's a huge proportion of the scores are actually around this area. So we would not reject the null hypothesis because this is a pretty normal score. But what if you guys got a 60, right? A 60 would be 3 standard deviations below the mean, right? Way over here, okay? Then we'd say, wow, if my students were just as good as everybody else, they wouldn't be scoring this low, right? So I'm going to reject the null hypothesis that my students are the same as everybody else, right? And I'm going to say, oops, I'm a terrible teacher and you guys didn't learn any statistics. Of course, it could be the opposite. Maybe you got a 90 and you're up here, and we can also reject the null. This is a two-tailed test, and we'll get back to that in a minute. Okay, so moving on. This area where we would reject the null hypothesis is called the region of rejection, okay? This just means that that whatever that sample mean or whatever that effect are so unlikely to be representing the underlying population, which is the null hypothesis, that we reject that they represent that population. So whatever we're comparing them to, so the null hypothesis, right? Criterion probability is the probability that defines samples as too unlikely. So we have to say, well, what do we consider unlikely? Do we consider it unlikely if it's only going to occur 5% of the time? Or do we consider it unlikely if it's only going to occur 1% of the time? Generally, in psychology and in most behavioral sciences, we set the criterion probability at That's an alpha at 0.05. And we'll get back to that next week. Okay, but just keep that in mind, 5%. So the critical value is just the value of Z that corresponds to that probability. So that defines the minimum value of Z a sample must have in order to be in the region of rejection. Okay, and for every value of Z, there is a corresponding probability value. A sample mean that lies in the region of rejection if its Z-score is beyond the critical value, either higher or lower. And we're going to see that in a minute. Now, when we're doing hypothesis testing, we're going to have what's called a rejection rule. And that's just saying what our criterion is and the critical value. Okay. So when a sample Z-score is greater than or less than the critical value, we're going to reject the null hypothesis that the sample represents the underlying raw score population, right? When it does not, then we're going to fail to reject the null hypothesis. Now, you'll notice if you read the textbook that they talk about retaining the idea that the sample may represent the underlying raw score population. So the key word here is may, okay? We cannot accept the null hypothesis, right? Null hypothesis significance testing does not provide evidence the null hypothesis is true. If you want to do that, you have to redesign your experiment or use Bayesian statistics. So I prefer to say fail to reject the null hypothesis, okay? Fail to reject, right? Okay. And like I said, every p-value has a corresponding z-value. Okay, so let's walk through that right here. So for example, if our decision rule is reject the null if p less than 0.05, remember that 0.05, that p 0.05. So if we have a two-tailed test, which is just that there will be a difference in either direction, we have to split that 5% up in the two tails, right? Actually, I have animations here, but I'm still going to do it. So for example, region of rejection for low values and for high values, right? It just means if Z is more extreme than, if we get values that are more extreme than whatever our criterion, which in this case is a P of 0.05, right? What does this mean? It means that critical value of Z is negative 1.96 and positive 1.96. So I've been telling you that 95% of scores lie within 2 standard deviations of the mean. Actually, it's a little bit more than 95% because 95% lie between negative 1.96 and positive 1.96. So what we do is we calculate a Z for our sample. And remember back in chapter 5, we've done a lot of calculating Z for individual scores, but now we're going to calculate Z for samples, right? And if we calculate that Z and it's greater than 1.96 or less than negative 1.96, then we can reject the null hypothesis. And these are the region of rejection right here, right? We make hypotheses that are non-directional. That's just, it will be different than two-directional tests when we're not sure. We think there's going to be a difference, but we're not sure whether it's going to be greater than or less than. For example, say, oh, well, I don't know. I'm teaching statistics and maybe my students are worse than the national average, but maybe they're better. Maybe I'm a fantastic teacher. So if I don't have any reason to believe that I'm better than or worse than any other teacher, I would make a two-tailed hypothesis and you would split that region of rejection, that 5% into 2. However, if I really believe that I'm a terrible teacher and I have good reason to make a directional hypothesis, then I would hypothesize that Z is less than or equal to, in this case, the critical value is negative 1.645. And this is because we put all of the region of rejection on the left side, the left extreme of the distribution. Now, if you're not really sure about making that hypothesis this way, you don't want to do that because this means that if it's the other way, you're completely wrong, right? Whereas if you make a two-tailed test, either way, either difference in between means is going to be significant. And we'll get back to that later. If on the other hand, I think I'm a great teacher, I might hypothesize that your scores are going to be greater than the national mean, in which case I'd make a hypothesis in this direction, okay, and say, I'm going to reject the null that you guys are the same as everybody else. if Z is greater than 1.645. Okay, so we'll get back to more of that next week.